Section 3.5. Prime numbers. Numbers, specifically integers greater than 1, are classed as either prime numbers or composite numbers. If the number is the product of two smaller positive integers, then it is called composite. Otherwise, it is prime. The first few composite numbers are 4 equals 2 times 2, 6 equals 2 times 3, 8 equals 2 times 4, and 9 equals 3 times 3. The first few prime numbers are 2, 3, 5, 7, and 11. The number 1 is neither prime nor composite. An important property of prime numbers is that any number can be written as the product of prime numbers in only one way, aside from the order of the factors. For example, since 30 equals 2 times 3 times 5, no prime number other than 2, 3, or 5 can evenly divide 30. Here, 2, 3, and 5 are called the prime factors of 30. The set of prime factors of any integer is unique. Determining the prime factors of an integer is called factoring or factorization. If two integers a and b have no prime factors in common, then they are called coprime or mutually prime. For example, 20 and 27 are coprime. If n is an integer, then n and 1 are always coprime, while n and 0 are coprime only when n equals 1. n and n plus 1 are always coprime. Using positive integers, when any number a is divided by another number b called the divisor, the result is a quotient and a remainder. Call the quotient q and the remainder r. Then q is defined as the largest integer such that qb does not exceed a. The remainder indicates how much is left over, that is, r equals a minus qb. Note that 0 is less than or equal to r is less than n. For example, suppose a is 40 and b is 11. The largest multiple of 11 that does not exceed 40 is 33. So the quotient is 3 since 3 times 11 equals 33. The remainder is 7 since 40 minus 33 is 7. Section 3.6. Modular arithmetic. The study of remainders is called modular arithmetic. Modular arithmetic was introduced by the mathematician Carl Friedrich Gauss of the University of Göttingen in 1801. In modular arithmetic, the quotient is ignored, the divisor is called the modulus, and the remainder is called the residue. In the preceding example, the modulus is 11 and the residue is 7. If the modulus is n and two numbers x and y have the same residue, we say that x and y are congruent modulo n, or equivalently that x and y are in the same residue class modulo n. This is written as x is congruent to y mod n. For example, 40 is congruent to 7 mod 11. So 40 and 7 are in the same residue class modulo 11. X and y will be congruent modulo n whenever x minus y is a multiple of n, or equivalently whenever x equals y plus an for some integer a. Residue classes follow the same rules of arithmetic as ordinary integers, such as: we call minus a the additive inverse of a. The notation a minus b can be considered shorthand for a plus brackets minus b. The situation for the multiplicative inverse is more complex. The congruence ax is congruent to b mod n has three cases to consider. 1. When a and n are coprime. 2. When a and n have a common factor d that does not divide b. And 3. When a, b, and n are all divisible by the common factor d. 1. Suppose that a and n are mutually prime. Then there is a unique residue a prime that is the multiplicative inverse of a modulo n, so that a prime is congruent to 1 mod n, and a prime a is congruent to 1 mod n. If a prime exists, then the congruence ax is congruent to b mod n can easily be solved as x is congruent to a prime b mod n. In section 15.3.2, I present efficient ways of computing a prime when n is large. 2. If a and n have a common factor, d, which is greater than 1, then a has no multiplicative inverse modulo n. There can be no a prime such that a prime is congruent to 1 mod n. If b is not divisible by d, then ax is congruent to b mod n has no solutions. For example, 4x is congruent to 5 mod 12 has no solutions. 3. Suppose d is the greatest common divisor of a and n, denoted GCD brackets a n. That is, d is the largest integer that evenly divides both a and n. If a, b and n are all divisible by d, then you can reduce the congruence by dividing a, b and n by d, namely, brackets a over d times x is congruent to brackets b over d mod n over d. Let's look at an example. Consider the congruence 8x is congruent to 4 mod 12. Dividing through by 4 gives the reduced congruence 2x is congruent to 1 mod 3. The solution to this congruence is x is congruent to 2 mod 3, meaning that x can be any integer of the form 3n plus 2. Going back to the original congruence, x is a residue modulo 12, so x must lie in the range 0 to 11 inclusive. The numbers of the form 3n plus 2 that fall in this range are 2, 5, 8 and 11. This means x can have any of the values 2, 5, 8 or 11. So the congruence 8x is congruent to 4 mod 12 has 4 solutions. Later in this book, mod is used as an arithmetic operator. The expression x mod y, where x is an integer and y is a positive integer, means the remainder when x is divided by y. Thus, 27 mod 3 is 0, 27 mod 4 is 3, and 27 mod 5 is 2.